Okay, let's start with Chapter 11, Sections 1 through 2. Go read those sections in detail and prepare yourself to apply the concepts learned to these questions. Concept questions 1 through 4 and 7 and 8, and exercises 3, 18, and 15. So starting with concept question 1, we have a variety of different boxes of different masses and moving with different speeds. I'm going to go ahead and just start with the first one. Say the momentum of the first box is equal to mv. Okay, so m, as given the problem for that one, is 20 grams, and v is 1 meter per second. So I'm going to just relate everything to 20 grams and 1 meter per second. Okay, so with that being said, PV in terms of mv is what? Okay, B is the same mass, but it's twice the speed, so 2v, which tells us, oh, okay, that's twice the momentum of the first one. Okay, go ahead and kind of follow that process for the rest of the boxes. Okay, as you do, PC is half the mass and twice the speed. So we have 1/2 m 2v, which gives us the original momentum. What about PD? It is half the mass and the original speed. It gives us 1/2 PA. And then what about E? It is 10 times the mass and 1/10 the velocity of A, which means that's the same thing as A. So here we have an example of a small thing moving at a decent speed and a huge thing moving at a slow speed having the same momentum. All right, let's move on to number 2. Go ahead and take a look at number 2. Okay, we have a 2 kilogram object that's moving with a certain speed, 1 meter per second, and then experiences this impulse of 4 Newton seconds. How is impulse related to momentum? Okay, we know that the change in momentum is equal to the impulse. And we could write this change in momentum as P final equals P initial plus the impulse. By doing this as final minus initial and add the initial to the other side. So we know what our initial momentum is. It's 2 times 1. And our impulse is 4, which means our final is 6. And since these are all positive, and we've assumed moving to the right is positive because we chose to use a positive 2 here, that means that the particle is moving to the right and faster. This is the momentum which leads to the velocity, with the particle being a mass of 2 kilograms, which divide this by 2, is 3 meters per second. Okay, so go apply that same idea to number 3. Okay, number 3, our initial momentum is the same, and it's moving to the right, but now we have a negative impulse of 4 Newton seconds. And so when we do this, we end up with a negative 2 Newton seconds, or a kilogram meters per second. And that means it is moving to the left with a velocity of negative 1 meter per second, again, because the particle has a mass of 2 kilograms. Okay, so again, the idea of how is momentum related to impulse. Take a look at number 4. And number 4 is a cool problem. It makes you think, and you can think about this in the hard way or the easy way, but apply momentum and force is what we know about impulse. We have a lightweight plastic cart and a heavy lead cart that are pushed by equal forces for equal amounts of time. And it's asking what is the momentum at the end of that time? Is it equal? Is one bigger than the other? How can you tell? So remember that delta P is impulse, which impulse is a force times a time interval. And in this case, the force is constant, so I don't need an integral sign. Just a total time times that constant force. And we're told the force is the same, the time is the same, which means the change in momentum is the same. And since they both start from rest, their final momenta is the same. Now, their final velocities wouldn't be the same because they have different masses, but their final momenta is the same. So P1 equals P2. for in their final states. P1 final equals P2 final, because these are the same. So that is an example of a powerful application of this process. If you tried to use this with previous techniques, we'd have to use kinematics to find out certain parameters, find the acceleration, and so on and so forth, and compare those. It would have been a pain. But with conservation of momentum, knowing how it's related to time and force, we could solve this really easy. All right, well, let's go ahead and skip now to number 7. Okay, this is a good question to really think, do we understand this relationship, this impulse-momentum relationship? So it's a lot more comfortable to catch a baseball with a mitt than with your bare hand. Why is that? How can you apply this principle to answer that question? Okay. The non-physics answer is, well, duh, it's padded. But what does padding do? Okay, when you're designing a mitt, you need to use physics to design that mitt. Okay? What padding does is it's changing the momentum of the ball. Whether I catch it with my bare hand or with a glove, with the mitt, it's going to stop. So the ball was moving and it stops. So in either case, mitt or bare hand, it's going to have the same change in momentum. Okay? But hurt is force. When I feel that force, it hurts. And so this equals F delta T. Well, when I have padding, that means it takes time to squish. So the stopping power takes more time, which requires less force. So with the mitt, the time goes up, causing the force to go down relative to the bare hand. With the bare hand, it hits the skin immediately, so delta T is super small, and therefore the force must be big, which means it hurts. So this is, again, a really cool question of applying that. Okay, let's take a look at number 8. Why do cars have crumple zones? Read number 8. So cars are designed with crumple zones. That means built into the body of the car, there are places where if a car hit, it will purposely crumple. Why is that? Why did they want the car to purposely crumple? Why not have it super rigid? Well, the reason is because if it was super rigid and someone ran into you or you ran into something else or a wall, it would just stop dead. It would stop immediately, which means our delta T would be crazy small, which means the forces would be really big because the change of momentum would be the same. If you're moving 3 meters or 30 meters per second and you come to a stop because of either, because of a wall with or without crumple zones, you have the same change of momentum, which means if you've got a rigid chassis, the force needs to be super big to accommodate that small change in time. But a crumple zone allows a larger time to occur, allowing the force to decrease dramatically. So again, awesome applications of this simple principle. All right, let's move on to some numeric exercises. Take a look at exercise 3. I'm going to draw it while you're going to explore that. Okay, so we have an object, a quarter kilogram, a 250 gram object that's being acted on by this force. Okay, the question is, what impulse is imparted on that object? Well, how do I find impulse from this graph? Impulse is defined as the integral of f dt. Okay, and in particular, we need to remember it is a component. That's why we have an x up here. So we could only look at the x component of the impulse. But what is an integral? It's an area under the curve. So what's the area underneath this curve? Well, I see a triangle with height of 1,000 and a base of 4. So this is going to be equal to 1/2 times base times height. So 1/2 4 times 1,000. And then I see a rectangle that's got a height of 1,000 and a base of 2. 6 minus 4. It's going to be plus base times height, which is 2 times 1,000. So I get 2 times 1,000 plus 2 times 1,000. So that's 4 times 1,000. So that's 4,000. Newton seconds, or kilograms meters per second. Okay. And so again, this is basically applying that definition. What is impulse? And we could then ask a different question. Well, if the object was moving so fast, how fast is it moving after this interaction? By applying the impulse to our change of momentum. Okay, let's move on. Number 8 now. Okay, we have this particle. It's originally moving, so this particle is a 2 kilogram object, and it's originally moving at 1 meter per second. Okay, to the right. It's moving to the right at 1 meter per second. All right, and then it experiences this force. Okay, so this is a constant force for a short window of 1 second. How fast is it moving afterwards? Okay. So how do I use this graph to be able to answer that? Well, it's based on the same ideas as this one, only we take it the one step further. So what's the impulse of this? The impulse is just the area under the curve, but we can see that is a negative. It's a negative area, so it's a negative 2 times 1, so it's a negative 2 Newton seconds. And so I can write P final equals P initial plus J, and my initial momentum is 2 times 1, so that's going to be 2 plus negative 2 gives me 0. So that is a sufficient force over a sufficient time, or in other words, a sufficient impulse to stop this 2 kilogram object moving at 1 meter per second. The last one, 15. Okay, this one's cool. This one kind of maybe trips you up a little bit, but it's a cool problem to really refine our understanding of momentum. Okay, in an initial case, we've got this cart with a mass of 10,000 kilograms. This is a railroad car, and it's moving at a speed of 2 meters per second. Okay, and then it gets a 4,000 kilogram load of gravel dumped down into it. Okay, and I ask, is that an insignificant force? That's a crazy big force. And it may even take a few seconds for it to happen. So does that mean our impulse is super small? The answer is no, it's not terribly small. Crazy big force over a couple seconds maybe to dump that load of gravel. So this isn't small. Does that mean momentum is conserved? The clue here is that these are vectors. So the impulse in the y direction from the gravel was pretty big. But what about the impulse in the x direction? It's nothing. There was no forces acting over any significant time there. And so the momentum in the x direction x final, x initial, jx. Okay. So the momentum in the x direction is equal to momentum in the x direction initial plus any impulse in the x, but there was none. Therefore, it is conserved. So we can apply that. So we just say, okay, well, what's m1? Therefore, what's v1? So our final will be m1 v1 equals m0 v0. And v1 is then m0 over m1 v0. Plugging in our numbers, we have 10,000 kilograms over 14,000 kilograms, because the new cart plus load is 14, and then times our 2 meters per second originally, and we're going to get 20 divided by 14, or 10 divided by 7, and that's going to give us a 1.4 meter per second final speed. And that makes sense because, one, it's similar to our initial speed, okay, so it's of the right order, but two, it's less than, it should be less than, because I have more mass to move, okay, and so it should have slowed down to compensate. All right, so that is the end of this class activity.